What's up, folks? So today we're going to continue the implementation of the joint image-text rectified flow model. To do that, we need to implement something called FiLM, which will add a type of global text conditioning. FiLM is not exactly for that. It's not specifically for that. It's a general model. It's a general deep learning technique, but we're going to use it in our case to implement global text conditioning. Okay, so let's just jump right into it. I'm going to show you the diagram for FiLM. So, okay, remember, this is our joint image text rectified flow diagram. You can see that we get the caption from this data distribution, we send it through the FLAN T5 encoder, then we corrupt it, and then after we pool the embedding by just doing a simple .mean operation, we're going to send it into this FiLM module. And we're going to, that combined with the time embedding, we're going to use to perform what's called FiLM. So this is FiLM. Essentially, we have our time embedding and our token embedding. We concatenate them, then we project it into 2 times the image dimension, and then we split it here. After the projection, we split it into beta and gamma, which are both of size the number of channels, the image number of channels. And then here we do an affine trans. So let me back up. So what FiLM is, in our case, it's going to be a way to modulate the image feature space based on the text tokens, on the pooled text tokens. Okay, so what that means is we are going to, so if you look here, this is an affine transform, right? We're multiplying the image embeddings by a gamma, and then we're adding an offset. We're adding a beta to it, right? So this is your standard affine transformation. And what affine transformation does is it changes, right? It's matrix multiplication plus a beta, right? Plus the offset. But this is essentially changing the geometry of the image embedding of the feature space of the C dimension, right? So what that means, we're changing the dimension of the feature space conditioned on the pool text tokens and the time embeddings, but the more important part in this case is the text tokens, right? So this is our text conditioning. Based on the prompt that we text in, we encode the prompt into text tokens. Then once we pass it through this projection layer, we're gonna get out some beta and gamma, and we're gonna use that specific beta and gamma, right? That's based on the text tokens to change the geometry of the image embedding, change the geometry of the feature space. That is text conditioning. It might take a second to sink in, but we are changing the geometry of the image features based on the text. That's FiLM. That's FiLM in a nutshell. So let's implement it. Let's just jump right into implementing it, right? So, well, maybe to drive the point home a bit more, remember, this is optimization. So we're saying that to improve the loss, right, such that to get the model to produce a result that matches the training image the most, we're going to modulate the image feature space, right? We're going to use an affine transformation to change the geometry of the image feature space based on a global text, on the pool text tokens, right? And we're saying that will help to decrease the loss. So let's get right into implementing it. So we're gonna put this diagram we're just going to code based off of this diagram right here. So I did add some to-dos, right? We need to implement cross-attention film, double ResNet block, and ADA group norm. Actually, I'm not going to do ADA group norm. It's just film plus normalization. But so in this case, we're just going to do film. So class film constructor self. What do we need? Image dimension, text, the text dimension, image dimension, time dimension. Always call the super. And now we're going to add this projection layer. Okay, this is going to take it. Okay. So we're going to concatenate. So let's kind of like stub this out. Def forward self pool text tokens, image embedding, time embedding. Okay. So let's see, pooled text tokens are going to be of shape. And then the text B batch and text hidden dimension, and then image embedding is going to be of shape B, C, H, W, right? Classic. Okay. And first thing we want to do is say torch.cat. We're going to concatenate the pooled text tokens and, right? So right here, the pooled text tokens and the time embedding, actually. So what are the dimensions of the time embedding? Time embed B, and then time dim, right? So, okay, so this is going to result, this is going to be on dim -1 or 1, whichever, right? This is going to be TH plus time dim, okay? So, and then we're going to have a projection layer that takes in this H, right? So self.proj projection takes in H, and it returns something of dimension B, C times 2, 1, 1, right? So B, C times 2, 1, 1. I'm going to condense some steps, but I'll do that after. I'm going to expand them and then condense them. So, okay, so projection, if we go back up here, projection equals nn dot sequential, nn dot linear, and then we're going to do nn dot, and then nn dot linear, okay? You've seen me do this pattern many times if you've been following along with my content. Okay, so so what's it taking in? It's taking in H, which is a shape TH plus time dim, okay? So we know that linear works on the last dimension of whatever tensor you pass in, right? So it's gonna work on this TH plus time dim, okay? So TH is our text dimension, text dim plus time dim, and that's going to go to hidden. I need to add this hidden dim, okay? We're going to expand it to some hidden dim, and then we're going to apply some nonlinearity, and then we're going to do hidden dim 2 times the channel dimension, because this beta and this gamma are the result of splitting the tensor that we get out of this projection later. So we're going to do 2 times image dim. Oh. Okay. All right, cool. So this gives us batch channel C times 2 because an image embedding is C, right? And then 1 1. Okay, cool. So this is gonna now we'll say H is this, and then to get, by the way, I just learned that I don't know, I'm so late to this, but I really enjoy using the Greek letters in Python code instead of having to type them out. So I just learned I can switch my keyboard to Greek and do beta, gamma. Like, wow, incredible. Then I can switch back to US. So I'm gonna say beta and gamma are equal to chunk, which chunks basically we're going to split our tensor, right? We're going to split along the first dimension. So chunk first dimension, and this is going to return B, C. Actually, this is I skipped a couple steps in this diagram. This beta and gamma are the result of chunking and then also chunking and then expanding. The chunking and expanding is implicit in this diagram, and I'm going to make it explicit here, okay? So this is BC, and so we're going to have a set, right? This is a tuple of BC, BC, okay? Cool. We can let's just return beta. We can actually just let's fill out the main method down here so we can just test it out. So BCHW, in this case, because we're going to put film in the mid block of this new UNet joint. We're going to put it here. So let's just do like a simulation where the mid block, the number of dimensions we'll say is 1024, just like we have here. Okay. So for the test, we'll say mid is 1024, and then it's downsampled by the time, it's downsampled by the time it gets to the mid block. So let's say it's like an 8x8 image, right? So 4024, 88. And then we'll keep L and TH the same. TH is the text hidden dimension. Actually, let's just make it's going to be 512 because we're using FLAN T5, right? Then we need, we'll redo all these. So the image, boom. We only need one time. Let's just call it time embedding. And it's going to be, this is the shape. Boom. And then X image. And then X text is going to be, yeah, that's right. And model is going to be film. Did I give it? Text image time hidden. Text dim. Text dim is gonna be TH. Image dim is gonna be, wait, I feel like something's off. It's not picking up. Wait, right? In it. Yeah, okay, that's fine. Text dim, TH, image dim, C, time dim, It's up here. We'll just bring it down here. Why not? Let's just call that TD for time dim. Time dim. And then hidden we'll say is we'll say it's 1024. I think I'll make it that when we're actually coding the rectified flow, the joint rectified flow model as well. Okay, so then model, what does it take in? Pool text tokens, image embedding, time embedding. Okay, so first of all, pooled text tokens is going to be x txt t dot mean, and then we want, it's supposed to be, it's supposed to be, right? So we have the text tokens, we have like, you know, so the text tokens are of size B, L, TH, and we want to average along, we want to average, so we'll end up with one text token that contains the average of all L, right? So we average along the first dimension. Boom, this should give us B, TH. Okay, so this is pooled text tokens, and then we pass in an image embedding and a time embedding. Okay, so then X, image T, and then time embed. Okay, and this will be out, and we'll print out dot shape, out dot shape. Okay, so it should print just the dimensions of beta, but let's just place a breakpoint here, step through it just to see what's happening. Like unexpected keyword hidden dim. Okay. Okay, pooled text tokens dot shape 4 by 512. That's as expected. B by TH. Image embedding dot shape 4 by 1024 8 by 8. That's as expected. Time embed dot shape. Okay, yep. So now when we concatenate, H should be 512 plus 16. H dot shape 512 plus 16. That looks good. And then self dot proj should take in 528 and then 1024, then 1024 to 2048, right? So we can split this beta and this gamma. H dot shape, yep, that looks good. Torch dot chunk, tensor, oh, the number of chunks. Okay, so we want 2 chunks and we want it to be along the last dimension. So then this, so we run this. So beta shape, boom. So this looks good. Okay, so then now we need to do the affine transform. Okay, so we'll do out is, actually let's just return So, okay, we have beta and gamma are both of shape B by C. So we need to make them B by C 1, 1. And if you remember from my last videos, right, because we need to broadcast, we need to do a broadcast operation across the image embedding, right? That's how we modulate the image token. That's how we modulate the image space. That's how we change the geometry of the image features. So we're going to broadcast beta across the image embedding. But in order to do that, we need to make beta and gamma across the image embedding. But in order to do that, we need to expand it, right? So instead of using the expand method, I just usually like to go, right, none and then none. And in this way, PyTorch knows to make a tensor of shape. So this will be of shape BC1, 1. Okay. And then I do image embedding times 1 plus that, right? And then I can do this, boom. Gamma, beta. Boom. Okay, that looks good. It's gonna be B, C, H, W. So now we have our modulated image tokens or image features. We have our modulated image features. So if we run this, we should get BCHW. Out should be BCHW. Yep. 4024, 8 and 8. So that's it. That's film. And then, so let's, while we're here, let's just wire it into, so we've done film. Let's wire it into our joint. Self dot film is film text dim 512 image dim 1024 time dim. What are we making time dim? Oh, we actually text dim. Wow. Yeah, okay. Time dim is time dim hidden is, let's make it 1024. Okay, cool. Move that to do. Okay, and close this. Cool, so then we'll copy this. We're gonna add film. We'll copy this. Boom. Then we'll do self.film. Cool tokens, X image T. No, this is gonna be M. We're in our middle layer, right? So let's switch back to our other diagram. So we're in our middle layer. So we're taking the result of UNet layer in the middle, and we're taking in the pool text embeddings and the time. Right, so then we have time is T embed. So T embed, and then X image is going to be what's coming out of the UNet layer in the mid block, which is M, which is of shape B 1024 4x4. Okay, so then, yeah, if we go to our, okay, so we can bring those over here. We can expand this. Live models, no, training. So from our last video, we left off with this. So if we run this in debug mode, and we put a breakpoint here, import error, UNet joint, train UNet pixel space live, cannot import name UNet joint. Oh, I modified the wrong file. UNet pixel space live. Train UNet pixel space. Oh, this is train UNet pixel space, sorry. Okay, kill this. Train UNet pixel space joint live. This should bring us to our class here. Yep, okay. Places breakpoint here. Okay, so oh, this should be hidden dim. No. Wait. Put this here. That's what I need to be running. Run. Boom. I guess I had another break point. Let's continue. Okay. Pool text tokens. Let's just step over it, see what happens. Yep, looks like it works. M.shape. Perfect. All right. That's it for film. Next video, I think we already have all the components. Actually, next video we'll implement cross attention because that's something that I haven't done in any of my videos yet, even though it's similar to self-attention. The only difference is, I'm just passing in another modality instead of doing one modality with itself. We're doing one modality crossed with another modality. But I'll do it. I'll implement it. And then after that video, we'll just fill in the rest of UNet joint. And then I'll show you the results of the runs. Okay, thanks for watching.